Hello everyone, my name is Stephen Bingham and I'll be presenting the topic Windows Azure Storage. I'm actually going to go over a paper which was created by some employees at Microsoft. Here's a quick overview of the presentation. We are going to start with what the paper is all about. Then we're going to go over why we need this high availability storage in the cloud. We're going to briefly go over how WAS or Windows Azure Storage cloud solution provides this, and also look at two other popular storage platforms. We're going to discuss Microsoft solution at a high level and also go over some of the design choices, and as well as how Windows Azure Storage performs against the competition. We will end by evaluating if the solution delivers on what is promised, and in our conclusion. Okay, so the title of the paper is called Windows Azure Storage, a highly available cloud storage service with strong consistency. And the paper was put together by a gentleman by the name of Brad Cadler, who was the general manager of Windows Azure Storage at the time, as well as 26 other authors. The paper can be found at the link at the bottom of the screen. So what does Windows Azure Storage deliver? Well, according to the paper, the Windows Azure Storage solution provides high availability and consistency. The authors discuss the architecture design at a high level of detail, and they demonstrate how it performs in the real world. What's interesting is that the authors also claim that not only does Windows Azure Storage provide availability and consistency, but also partition tolerance in certain scenarios within a region, which we'll go over. And that the CAP theorem states that this is impossible to achieve, or it's impossible to guarantee all three properties at the same time. This is very significant, not only from a theoretical standpoint, but from a practical perspective as well. You'll see from a theoretical standpoint, the CAP theorem states you can only provide 2 out of 3 properties at best. And from a practical point of view, it's very important for customers to be able to have a service that can achieve these properties, even high availability and consistency would be great for customers, but to be able to provide all 3 would be fantastic. And this is very important for enterprise customers that typically have to support mission-critical applications that are spread across several regions or the globe. So before going into detail about what Windows Azure Storage is, and look at the CAP theory, what it is, and its properties. At the high level, it's basically just a theorem that states that you cannot have all of these 3 properties at the same time in a distributed computer system. You can get at best 2 out of 3, as you can see from the diagram here. Um, so what is availability? Availability is that every operation request receives a successful response given. So for example, you can have a write operation and you know we would want the system to be able to process that write operation successfully and return a response. Consistency means that if you have more than one node, for example, as to distributed systems, so you'll have more than one node, and if you process the write operation, for example, we would expect that both nodes have the same data. So for example, if I send a request to store a data object which has a value of 10, for example, just for simplicity. If I then do a read across a different node, I should expect to receive 10 and not 11, for example. So all nodes should see the same data at the same time. That's consistency. Partition tolerance has to deal with when you have two different nodes, partition tolerance means they should work even if they're not communicating with each other. For some reason, maybe there is a network failure, well, you should still be able to access either node. And you can have situations, it's quite common to have situations where there's high traffic or network failures to be able to have this miscommunication between nodes. So it's important to have this partition tolerance. So need high availability in the cloud. What's the motivation for WAS, Windows Azure Storage cloud service? Well, comes to mind is mission critical applications, such as stock market, the global banking, or e-commerce. There may be a need to store large amounts of data near customers for performance, or across multiple regions for disaster recovery. And Windows Azure Storage allows customers to store exabytes anywhere across its regions, which is US, Europe, and Asia. And does this by providing a global namespace, those data to be stored and accessed in a consistent manner. We're going to see more of this in subsequent slides. And disaster recovery is another feature which Windows Azure provides, Windows Azure Storage. And this is redundancy that's provided by storing replicas across multiple data centers that are hundreds of miles apart from each other. So that's a nice feature to have, which is built into this Windows Azure Storage. It also provides shared storage infrastructure that is somewhat isolated in terms of storage is its own service, and that same storage infrastructure is shared across many customers. And this makes it significantly less storage is required to actually, to be provisioned at one time than if we were using dedicated hardware, for instance. All right, so having an easy low-cost storage solution with DR support is very important for mission-critical applications. We are now going to look at two popular cloud storage options and why they are good or not good to use for mission critical. We'll start with AWS, which is an infrastructure as a service provision model. And here is an overview of the services. Now, we may not want to use AWS because of the provision model. It's infrastructure as a service, and while the cost may be what about disaster recovery? Is that included? Well, no. The answer is no. It doesn't come built in, and to have disaster recovery for the Windows Azure, for the Amazon, you would need to actually do a little bit of configuration. Now, there is some good redundancy within the areas where it's stored, like some very good redundancy in S3. But if you were to use EBS, you'd have to create your own processes to back up or replicate data. So the other reason is it's even in S3, it's not exactly it's not easy to just access that data as you would with Windows Azure. For example, in S3, you would have to use an API to write data, and these writes, they're only appends, and if you want to update an object, you're gonna have to actually overwrite it. You can't easily update pieces of an object. So, for example, if you store a movie on the S3 or a file system, you may want to update it just as a block within the file system, but that may be very difficult to do with S3. Actually impossible, because it only allows you to overwrite the data, not append. So it's not the best solution for our disaster, for our mission critical applications. What about Google Cloud Storage? This is a platform as a service, and it's probably more feasible. It has flexible access in terms of you can use RESTful APIs or BigQuery, Google App Engine, or Cloud Platform Services, for instance, to access data. It comes with OAuth and granular access controls for configurable security, and it has DR built in. The price is a bit cheaper than both AWS or Windows Azure. It also comes built with the redundant storage in multiple physical locations. Now, what it does not, or what it didn't offer, was the ability to choose where you want to store your data within regions, but that's something that's recently provided and is in experimentation. So, this could be an option for having mission critical applications. But what we're discussing here is actually Microsoft's solution, and it's scalable and elastic, it's auto-partitioned and global accessible. So what do these mean? Well, at a high level, scalability just means you can process hundreds of terabytes of data or small amounts of data. You could start small and then scale up, or you could start big and scale down. The important concept here is you pay for what you use. So whether you're a large corporation or a small business, you can use Windows Azure Storage for scalability. Elasticity refers to the flexibility of provisioning or deleting the storage or instances. So for instance, you can design applications for large global audiences like the financial institutions we discussed in this slide. Or you can, and you can pay for what you use and when you use it as well. So for example, in a big data application, you may want to analyze some market data to produce a report. And when that report is complete, you no longer have a need for it, you can delete or terminate some of the storage required to save cost. So that's very flexible. Now, auto-partitioning is great because you don't have to build solutions for partitioning data across regions, which is what we want. And again, it's globally accessible across its regions. All right, so we have 3 storage types: blobs, tables, and queues. Now, the blobs provide simple interface for storing named files, along with its metadata. A diagram here of a blob, along with a URI to refer to that blob. And it's structured storage. So a table is a set of entities which contains a set of properties. These are properties like name, you can have email, location, etc. And finally, provides reliable storage and delivery of messages for an application. So queue contains messages, right? All right, so those are the storage types, and here's a high-level view of the Windows Azure Storage. All right, so we have the URI at the top, and this URI will, the storage location server will take this URI and look up account information and authorization and route to different storage tabs wherever it is. So what is a storage tab? Well, a storage tab is a cluster of racks, a number of racks of storage nodes. And each rack is built out as a separate fault domain, which has its own redundant networking, its own redundant power. And the clusters range from 10 to 20 racks with like 18 disk-heavy storage nodes per rack. The system provides 2 replication engines. We have the interstamp replication, which happens asynchronously, and there's also the intrastamp replication, which happens synchronously. You see here that the interstamp replication happens on the partition layer, and the intrastamp replication happens within the stream layer. So we're going to discuss the stream layer. Here's some brief information on stream layer. Used only by the partition layer, and it's got file system like namespace and API access. Streams can only be appended to. The append operations are atomic. It's all or nothing. And here are some attributes that we'll discuss in further slides. Block, which is minimal unit of data. Extent is unit of replication in the stream layer. The stream layer has like 3 replicas within each storage stamp, and it provides automatic garbage collection. And also important to mention that the stream manager of the stream layer is as a Paxos cluster. So this stream layer is what we use to store bits on disks. So in essence, is in charge for distributing and replicating the data across many servers, right, to keep the data durable within that storage stack. And why do we use Paxos cluster? Well, we use this for solving consensus in a network of unreliable processes. Right? For example, you have a situation where if a master fails, then you have a new relator election. Here's a diagram of storage stamp architecture. Here we see at the stream layer, we have these Paxos cluster of storage managers which communicate, and they're in charge of keeping track of the stream namespaces and the extents across each stream. And these extents are allocated across extent nodes here. Right. So, the stream manager has quite a few responsibilities. Just going over responsibilities, it's like, for example, maintaining the stream namespace, the state of all active streams, extents, for monitoring the health of the extent nodes, creating and assigning extents to end extent nodes. They also perform lazy replication of extent replicas that are lost due to, for example, hardware failures. And as we mentioned before, garbage collection of extents that are no longer pointed to a binding stream. There's also scheduling and erasing of some maintenance of extent data that goes along with the stream policy. Now, the cool thing is that this stream manager actually pulls the state of these ENs, and may discover that one extent is replicated fewer than expected on a number of these extent nodes. And then this stream manager will take care of that. It will actually replicate the extent, choosing different ENs to store that extent. So it has to store different extents across different fault domains for redundancy. Right. So that protects our nodes against unexpected failures due to power or networking, and so helps with availability. So we see this layer we have a partitioning and availability. All right, so what is an extent node? Well, briefly, it's a component that maintains storage for a set of extent replicas, and that are assigned by the storage manager, right? And this really covers the stream layer. Okay, the next layer is the partition layer. briefly going to go over what this layer provides. And this layer, we're really going to take care of higher level abstractions, such as blob, table, or cube. And so it stores these different types of objects. Also provides scalable object namespace, and transaction ordering with strong consistency for objects. Now, the partition layer stores objects on top of the stream layer, and also provides caching of objects to reduce I/O. Disk I/O, because memory is faster than disk. All right, so another responsibility of this layer is to achieve scalability by partitioning all of the data object within a stamp. As described earlier, all objects are replicated or extensor replicated on the stream layer. These objects at the partition layer have a partition name. They're broken down into disjointed ranges based on partition name values and served by different partition servers. We're going to actually look on this architecture in the next slide. But the layer manages these partition servers with ranges for the blobs, tables, and queues. And the cool feature also is that it provides automatic load balancing of the partition names across these partition servers, as you'll see in the next slide. So here. All right, so that is the partition layer. And we're going to actually look at the next layer, which is the front-end layer. It's a layer that consists of a set of stateless servers that take incoming requests. So, for example, those requests that of a URI, an object that's passed through to a load balancer and it's forwarded to the front-end layer. Well, it will take that request and look up the account name, authenticate the account, and authorize. So decide whether they can request an object or not, or the levels of authorization. Then it will route the request to a particular partition server in the partition layer. Right, so the system also maintains a partition map that keeps track of the partitioning ranges that we referred to in the previous slide, and which partition server is serving the partition names. And the server also caches the partition map, and it's used to determine which partition to forward each request to. The front-end servers also stream large objects of data directly from stream layer and cache frequently accessed data for efficiency. So, and the architecture, and the million-dollar question is, how will we maintain 3-cap properties in this scenario? Let's look at the scenario where we have 2 storage stamps. We can see clearly that if there's a network failure between the 2 storage stamps, which is this interstamp geo-replication, well, what happens if that fails? Well, definitely we will not be able to guarantee any strong consistency as the author states. However, there's also interstate stamp replication happening within each storage stamp. So the next question is, can we achieve all 3 in a storage stamp? Maybe we can achieve it out of the storage stamp. What about in? Well, unfortunately, the authors don't really go into great detail to illustrate how the Windows Azure Store provides these guarantees, or there is no really diagrams that point out the different scenarios where you have failures between nodes within the stream layer, partition layer, or front end layer, and how Windows Azure guarantees the three properties on all layers, or as a whole. So definitely more illustration on how different networking failures or other failures, such as write operations within a stamp, would support partition tolerance while maintaining strong consistency and availability is required. All right, so the benchmarks. So overall, Microsoft Windows Azure Storage performs pretty well compared to its competition. For example, in 2013, there was a benchmark that was conducted by SU on Windows Azure Service, and it was the top performer in write speeds, outperforming any major cloud storage provider, such as AWS, Google, HP, or Rackspace. Here you see Microsoft at the top. What about the Read benchmark? Scored pretty well. It's the second, just behind Amazon. But interestingly, they also were number one for index reads, and that's very. So in conclusion, we see that Windows Azure Storage consistently performed better than any other cloud service provider writes, and was really good in the non-index reads second, and best in index reads. They were the only cloud platform also to post 0 errors during 100 million reads and writes. And that may be due to the amount of availability, the amount of replication, both region and within storage stamps. And we can clearly see that this solution, this Windows Azure Storage, is highly available and strong consistently within a storage stamp. And for the communication across regions, you can see that Windows Azure Storage does give you good partition tolerance, availability, but with eventual consistency. So not all three properties at the same time. This is the end of the presentation, and thank you very much.